to our monthly webinar series. For those of you who aren't familiar with IEEE, we're a membership-based nonprofit organization, provide our members with objective information and resources for renewable energy and energy systems integration decisions, peer-to-peer networking opportunities, information and knowledge sharing, and professional educational experiences. We held our VG forecasting workshop in St. Paul in June, and our next activity will be the fall technical workshop in Denver during the first week of October. This is a workshop on the full range of issues associated with integrating wind and solar into electric, gas, and thermal systems, and coupling to energy-consuming infrastructures ranging from transportation to buildings and water, assisted by data and communications. Registration is open. Everyone's invited to attend. IEEE is really quite a unique organization, and I don't think you'll find anything quite like it anywhere else. If you're new to IEEE, I strongly encourage you to follow up with us if you like what you hear, and I think you'll be pleasantly surprised. You can find us at www.iseig.energy. Okay, just a few logistical matters, and then we'll get started. First of all, phones will be muted for the duration of the webinar to avoid unnecessary distractions. So please use the question and answer box on the lower right-hand side of your screen to submit questions, and we'll save 10 or 15 minutes at the end for the Q&A. We plan to wrap it up at the top of the hour, and an email with a link will be provided once the presentation and the audio file have been posted. Okay, so today our webinar will feature Babak Enayati from National Grid. Babak received his PhD and EE from Clarkson University in Potsdam, New York in 2009, and he's currently a lead engineer at National Grid and a senior member of the IEEE. Babak serves as the vice chair of the IEEE Standards Coordinating Committee, SCC 21, and IEEE 1547, the standard for interconnecting distributed resources with electric power systems, which he's going to talk about today. So Babak came up through the ranks as a protection engineer at National Grid, and he's been involved with distributed generation and distribution system protection since he joined in 2009. I've only known Babak for maybe the last 5 years, but I can tell you that he knows his stuff, and I've come to greatly value the contributions that he makes to the industry. We're very fortunate to have him here with us today. And on a personal note, he can't be all bad because I found out last night that we have 154 common connections on LinkedIn. Go Babak. So today Babak will present a brief overview of the IEEE 1547 standard, which governs the interconnection of devices to the distribution system. With the rapid expansion of DER in markets all over the world, there's intense interest in the most recent version of IEEE 1547, which was approved earlier this year. The previous version of this standard dated from 2003, and a lot of change has happened since then. So we'll focus on the new standard, particularly concerning the new requirements for voltage and frequency ride-through, frequency control, and steady-state voltage regulation. Implementation of the new requirements will be covered using Massachusetts as an example, including the adoption of ride-through and challenges of implementing voltage regulation. Okay, so without any further ado, let's go ahead and get started. And Babak, I'll now turn it over to you.
Excellent. Thank you, Charlie. Can you hear me?
Yes, we can hear you.
Excellent, excellent. Well, thank you so much, Charlie, for the introduction. And hello, everyone. Good afternoon. And folks on the West Coast, I guess, good morning still. So I'm Babak Enayati, and I will be today talking about the IEEE 1547 implementation experience, I should say. So as Charlie mentioned, the standard was published recently. Just to give you the exact date, I believe it was April 6th, 2018. And industry has been trying to first understand the standard and also implement it properly so that it does not adversely impact some of the current practices that we have in the utility business. So I will walk you through some of the, I would say, implementation processes that we went through in Massachusetts, where we are seeing high penetration of solar generation, and then we'll take some questions in the end. So we basically started the partial implementation of the standard, started off with right-through concept, and then we're also in the process of working on voltage regulation and frequency regulation as well. So I'll give you an update on all areas where we're working on. So with that intro, so let's move on. Just to list the topics that I'm going to cover today. First, I will start off with abnormal performance categories that were introduced in the standard, the 1547 standard. Just to make sure, we're all on the same page. I know most of you already know what right-through is and which categories were introduced in the standard. But just to, as I said, make sure we're all on the same page, I'll do a quick overview of the categories. And then we'll move on into basically the experience in Massachusetts. First, you'll see the driver for some new right-through requirements in New England, and also what was the interim solution in Massachusetts until we see a fully revised 1547.1 standard published. So until then, we really won't have any equipment that is certified by NRTL, basically that meets the 1547 requirements, but there is an interim solution that we implemented in Massachusetts to meet the right-through requirements that were basically requested by ISO New England. And then finally, I'll also talk about the plan in Massachusetts on how to basically implement the rest of the standard. So starting out with right-through, how about voltage regulation, frequency regulation, and so on. So moving on to the next slide. This table lists the three categories that were identified in the 1547 standard. Let me give you a little bit of background on why are we even thinking about the concept of a right-through, or I'm sorry, the categorization for right-through. If you compare, say, a synchronous generator with an inverter, and then you put, say, 50% under voltage on the terminals of both, the synchronous generator will have a limited capability to withstand that under voltage by 50% for an extended period of time. Okay, it can become unstable and overspeed and so on. Whereas the inverter technology, they really don't care what the under voltage value is. As long as there is a voltage reference there, they can withstand it and stay on for an extended period of time. So the point I'm trying to make is technology matters when it comes to the characteristics of the DER type. So rotating machines versus power electronic based technologies. So the whole idea of 1547 was we have to remain technology neutral. So coming up with one set of requirements that meets both rotating machines and inverters and stay technology neutral was really almost impossible. So what we did, we categorized the requirements and said, well, why don't we just start with category 1 for DERs that meet the basic bulk system needs from reliability perspective, and then category 2 and 3, move on to some of the requirements that are mentioned in NERC PRC 024, and some that may address FITVER events, fault-induced voltage recovery events, and also category 3 would be more advanced requirements. When I say advanced, meaning wider range for trip, plus the right-through capability itself. And so we referenced, say, used documents like California Rule 21 and Hawaiian Rule 14H. So this was the idea behind this categorization, that we wanted to make sure that we come up with some requirements that cover most of the state-of-the-art technologies, with rotating machines and inverter-based technologies. So we have three categories for write-through. Moving on to next slide. I just put an example of what you're going to see in the standard when it comes to voltage write-through. This is just a category 3 voltage write-through figure. Of course, you're going to see one for category 2 and one for category 1, but the whole concept is the same. We want the general DERs stay on, support the grid during bulk system disturbances. And so let's just go through this figure for a second, just to make sure we can all understand how to read basically this figure. So let's start with the two blue points, 1 and 2, and the red. These are the default values for trip, okay? And so for blue, like for example, number 2 here is like 50% trip at 2 seconds. That's the default. The arrows show the ranges of adjustability. So of course, some of the requirements that you're going to have a write-through in some parts of the country may be a bit different than the other parts due to like penetration of renewable and and plus, some countries as well that are adopting 1547 may not be happy with those default numbers. So the arrows are there so that the engineers can request like a different setting for trip. Then if that requested setting is within this adjustable range, the DER still remains NRTL certified. So you're not violating the certification by changing those trip points. The write-through itself is a capability. It's not a trip. So if you look at this figure here, the green area says do not trip. It's like a continuous write-through requirement. So it the continuous operation of the DER. So if the voltage is between 110% to 88%, the DER will remain connected and produce power. The mandatory operation, the concept is similar, and the only difference is there's a limited time for that mandatory operation. And the other area that has been recently or has been introduced in the new standard is called momentary cessation capability. This is mainly applicable to categories 2 and 3. The idea is that more like inverter-based technologies have this capability that when the voltage goes below a certain limit, in this particular case as a default is like 50%, the voltage goes below that, inverters stop producing current, but they're not physically disconnected from the grid. So once the voltage recovers and goes back above 50%, they can start producing current immediately. So right now there's this 5 minutes reconnection time and all that's going away with this concept of momentary cessation if there's no physical trip. So this is actually very important. The momentary cessation is something that we used in Massachusetts to resolve some of the distribution system protection issues, which I'm going to cover later on. So that's the reason that I put it in here, to make sure we're familiar with the concept. And then, the gray area is shall trip, which is self-explanatory, and I think that's it for this figure. So moving on to the next slide, for categories 1, 2, and 3, we only came up with one set of frequency write-through requirements. What you see here is the figure. There is a table in the standard associated with this figure, but I personally feel more comfortable presenting figures and tables and numbers. So if you're interested in looking at the exact numbers, you can refer to the standard and take a look at the table itself. But the idea is again, the same. We want the DER to stay on and support the grid during now frequency disturbances. So you see the green area is the continuous operation of DER for frequencies between 58.5 and 60.6 hertz. And then we have the mandatory operation with a limited trip time, basically, or duration. And also may write through, may trip, plus the shall trip regions. All right, so and then so the 2 blue points, 1 and 2, and the red, these are also the default values, and the arrows show the range of adjustability. So that's kind of like a background on what's being required right now for write-through in the new 1547. And if you're interested, again, more in like the details and the consecutive write-through and all those concepts, feel free to take a look at the standards. I'm going to move on to like the experience in Massachusetts now. What were the drivers, and then plus the adoption process. So ISO New England did a study in their service, in their territory, basically. What they did, they put a 345 kV fault, put a fault on a 345 kV line, and they showed us that the voltage, you know, and that goes below 70% in this particular example, like some like light blue areas, and even less than 50%, some dark blue areas. That's basically what they're showing, that in a very large area we will experience an undervoltage, a momentary undervoltage, and they're really concerned that with the high penetration of solar, especially in Massachusetts and other states in New England, we're gonna lose a large portion of DER on the distribution system. So they raised this concern with the utilities under Massachusetts Technical Standards Review Group, and I'll walk you through the adoption process later on. But one thing that you may ask and say, like, well, if I have a fault on a 345 kV line, well, the faults on the transmission system can be cleared pretty fast, way before even DERs may trip. So why are we even worried about this issue? Well, you're absolutely right that the undervoltage, the fault can be cleared by like high-speed protection, like, you know, you're talking about like a zone 1 of a distance protection, and the relay itself can trip immediately, plus you'll have just a few cycle, or maybe not a few, even like one cycle, or even like a fraction of a cycle for breaker operation on transmission system. So yes, the fault will go away, but the impact on the system can stay. Like, you know, because of the inductive characteristics of the grid, you may see like a voltage recovery of the system, you know, like kind of like in the low speed. Like a delayed type voltage recovery. They call it FITR, fault-induced delayed voltage recovery. So that under voltage condition may stay in the grid for a second, 2 seconds, depending on the reactive component of the inductive component of the grid. So, which can definitely cause DERs to trip. So that's basically the reason that, you know, ISOs are concerned, given the fact that we already have high-speed protection on the transmission system. So, so that's basically the driver. So the next slide, this is the projected PV growth in different states in New England, and of course the highest is Massachusetts, and that's where ISO New England started to this outreach and informing the utilities in the state that we need to do something with write-through especially. So you see that by 2027 we're expecting to see 3.6 gigawatts of solar only, and in total for New England area we're at projection of 5.8 gigawatts. And the trend that we have seen so far, the actual PV growth in New England is higher than ISO's projected PV growth. So the numbers you see here, when the actual PV growth is going to be a bit higher than what you see in this table. So which is basically worst case from write-through perspective. So moving on. What was the interim solution? Where ISO New England said, we cannot wait for the IEEE 1547.1 to be published. And just to give you a little bit of background on 1547.1, that's basically a standard for testing and conformance and compliance for DER. So if you, as a DER manufacturer, you say, you know, my generator is compliant with 1547, you have to make sure that, you know, it passes the test identified in 1547.1. It's a standard. It's not like a guide or recommended practice. And once we published 1547, most of the resources have been put on revising 1547.1, and we're in the process of the revising standard right now. The goal is to submit the first draft of the revised standard for balloting by end of 2018, and that will, based on the number of comments we'll receive, may take another 5 to 6 months to address all the comments, and then you know, see if we need another ballot, or we can just reach out to the you know, those who submitted comments and you know, ask for their votes again. So we need to come up with a process that would work for 1547.1. So the point I'm trying to make is, like, you know, maybe by mid-2019 we'll have something ready to submit to IEEE. They have to go through their own, IEEE essay, so they have to go through their own editing process, plus, which takes another like 3 to 4 months to get the standard published. Plus we have, like, you know, the NRTLs need another 5 to 6 months to revise their test regimens to adopt the new 1547.1. So the point is, ISO New England is concerned about that process and says, with the existing solar growth in New England, we really cannot wait till like 2020 or later to adopt the ride-through. They're already starting to see that, you know, when they have faults on 345 kV lines, they're seeing some the potential trip for some DERs with existing 1547 settings. What was the interim solution? The UL 1741 SA, or Supplemental A, was introduced as interim solution. Just to give you a little bit of background on what 1741 SA is, California last year, I believe it was like October 2017, they mandated the utilization of smart inverters in California. So it was like mandated by California PUC. And utilities were concerned that there's really no, they had the smart inverter working group, like in 3 different phases. They came up with some requirements that were put in Rule 21, but the utilities were concerned that, you know, we really don't have any inverters that meet these requirements, like that are certified and you know, comply with these requirements, that pass some NRTL testing and so on. So UL 1741 added a supplement to their test regimen that only addresses the Rule 21 settings, and Rule 21 both Hawaii and California, I should say. I don't want to skip Hawaii. They have their own also 1741 SA as well. But so basically they added this supplement and said, like, so this supplement certifies inverters to meet what's in Rule 21 and Rule 14H. And so ISO New England said, well, because we do have inverters that are 1741 SA certified, and ISO New England was also comfortable with the settings and the capabilities in SA, and so they said, you know, we accept utilization of inverters that are 1741 SA listed. So they reached out to the utilities through the Massachusetts Technical Standard Review Group, TSRG, which is basically a working group that state regulators, utilities, and DG customers and government folks attend to review the interconnection guidelines in the state. So they reached out to that working group and asked for, you know, a new mandate on ride-through in the state level. That's the background, and that's how we basically use 1741 SA as an interim solution. some of the settings that were discussed and agreed by the utilities. So you see the voltage trip settings here for like we require basically 2 over voltage, 2 under voltage settings based on the existing. The past 1547 plus the existing one. There are like 2 set points. Nothing changed really. It's just the settings. The settings changed. By the way, one thing that before I forget, I have to mention that the ISO numerals write-through requirements in Massachusetts are only for solar generation for now, and may be extended to storage in the near future because we are seeing higher penetration of storage as well. But they're not applicable to rotating machines because the penetration of rotating machines is low in the state. So with that clarification, so if you look at these settings, it was mainly the only change that I should say compared to the old 1547 is the under voltage 2, which is 50%. The trip, the clearing time we identified as 1.1 seconds, but this is also the mode that we're requesting or we're mandating is the momentary cessation mode for voltage below 50%. Okay, and what does that mean again? If the voltage goes below that limit, the inverters stop producing current and they go to this momentary cessation mode up to 1.1 second. If the voltage is recovered within that 1.1 second, then inverters start producing current and the system goes back to normal. But if that momentary cessation mode lasts for longer than 1.1 seconds, then the inverters trip. So with that, with all these settings, so let me explain the distribution utility's resistance towards adopting right-through. When I say resistance, there's like technical reason for that. On the distribution side, the DERs, well, let me rephrase that. If you have a under voltage condition and the DER senses that, it's supposed to basically ride through up to a certain limit. If that under voltage is caused by a fault on a transmission system, like a bulk system, then the DER has to ride through that under voltage condition. But if that under voltage is caused by a fault on a distribution wire, then the DER should trip. There's no ride-through requirement for a fault on a distribution system, and there shouldn't be because we want to make sure all the generators on that faulted circuit trip offline as fast as they can so that they don't impact the fault duty and arc flash and all other things that are very, the safety aspect that is very critical on the distribution side as well. So, but the generator itself has no clue what's causing that under voltage. The only thing it's doing is just measuring voltage, at either point of common coupling on the high side of the interconnection transformer, or in most cases, the point of DER connection is the low side. So either high or low side in a connection transformer is the voltage is basically the reference point, and the DER in general have no clue what's causing that under voltage. So there's an issue here. Protection folks on the distribution side and say like, well, what if I have a fault on a distribution wire and your DER doesn't have overcurrent protection, so it's only relying on voltage to detect the fault, and now the right-through says it has to stay on for a certain period of time. But on the distribution, we really don't allow that. We want generators and plus the utility source trip off as fast as possible. The momentary cessation mode really helped us with that discussion, and the reason for that is, as I said, momentary cessation is the mode that the generators stop producing current, okay? And most of the faults on a distribution system, if the fault impedance is not too high, will cause the voltage to go below 50%. Again, if the fault impedance is high, then you may not even be able to detect that with your regular overcurrent relays anyway. But most faults will bring the voltage on the distribution wires below 50%. And what does that mean? But based on this requirement, all generators that sense that under voltage below 50% will stop producing current, which is a good thing from protection perspective, that they're not contributing to any faults. They like immediately go to like idle mode. They're not doing anything to the grid, so they don't really adversely impact the system protection. And so this was actually the key function that relieved utility distribution engineers. Then they kind of like, they said, okay, so that's an acceptable function that assures or reassures that, the system protection, the distribution system protection is not going to be adversely impacted. Without that momentary cessation, there's a challenge. And for example, like rotating machines, if you're in a state where the penetration of rotating machines, rotating generation is high, you may be concerned that, yes, these generators staying on for a long time due to an under voltage condition may have an impact on system protection. So you may need to require some sort of like power line carrier technologies or something that would be used to detect distribution faults in addition to like overcurrent protection. So with that, I'm going to move on to the next slide. So this is basically the slide that we, the right-through capability that we mandated for Massachusetts. We picked Category 2 right-through capability table from 1547 because it's the settings that on this slide are actually within the range of Category 2 trip points, okay? So we couldn't do Category 3 because Category 3 did not have these trip settings, but Category 2 did. And so we were very comfortable with Category 2 requirements. So I'm not going to walk you through every single line on this table. The whole point was, based on the processes, talk to your distribution protection engineers, make sure that they're comfortable with the required right-through settings and capabilities, and then come to 1547 and pick the right table, or I'm sorry, pick the right category that offers those capabilities and plus the trip settings. That's basically the process. The key here is make sure protection and distribution protection engineers are comfortable with what your regional ISO is proposing for right-through the settings, especially the trip settings. Okay, because the capability is good to have, but really protection folks are concerned about the trip settings. So we're going to make sure that both parties are talking and coordinating these settings. Okay, so that's done with, that's with voltage right-through. With regards to frequency right-through, so these are the frequency trip settings. Based on the experience we had in Mass, really, we've been complying with NPCC Directory 12 under frequency load check curve anyway. So adapting these settings, the trip settings, really was not a big challenge and big deal for local utilities in the state. We are already compliant with these settings, so it was really not a big deal for us to adopt the ISO New England's requirements. So again, 2 over frequency set points and 2 under frequency set points. You see the settings on the slide. The capability, so you see like for frequency, this table is from the standard, 1547 standard. We have a continuous operation range, mandatory operation, and no right-through range. And again, it was pretty straightforward. We really did not have any sort of issues with frequency right-through because of currently adopting the NPCC Directory 12 under frequency load check curve. And we really don't use frequency relaying for protection anyway. So our protection folks were like, okay, so this is they really did not care much, you know, when it comes to detecting faults and so on. So, and the reason that we don't use frequency, frequency measurements for protection, more like, you know, some relaying manufacturers still using zero crossing point, and it can be tricked by, like, you know, noise in the system. I know some using advanced phase lock loops, but there are some issues with when it comes to utilizing frequency for faults. And when you do have a fault, really the system frequency doesn't change much after some transients. It's really not a good relay for fault detection anyway. Okay, so what's next? We just talked about write-through only. Of course, 1547 is, you know, the big standard, and like, you know, which covers voltage regulation, frequency regulation, islanding systems, you know, secondary network interconnections, and there's a big list like interoperability is another aspect. What's the plan for the future, or the near future, I should say, with regard when it comes to adopting the standard in Massachusetts? So let's start with voltage regulation. There are some voltage regulation, basically, like for those of you who are not familiar with this concept, the old 1547 to 2003 version said voltage regulation is not allowed by the DER, so the generators are only you know, mandated to just produce watts and make money for the customer, and you know, they can do constant power factor mode, off unity if the utility requires it and the customer is okay with that. When I say customer, the generator owner. But other than that, there's really no dynamic type voltage regulation. But the new standard mandated the voltage regulation capability, meaning that all generators, regardless of size and type, will have some sort of voltage regulation capability. But the performance will be at the utility's discretion. So the default voltage regulation capability is unity power factor, meaning that there's nothing enabled unless the utility requires that, basically, for their interconnections. So we in Massachusetts are in the process of revising, you know, reviewing our the 1547 voltage regulation requirements, and also revising our interconnection guidelines to include voltage regulation in it. There are some serious challenges when it comes to voltage regulations that we don't have that for write-through, so that's why the write-through adoption process was straightforward. One of the issues is impact on system protection, and we're still trying to understand. So when it comes to, you know, enabling voltage regulation, is this reactive power component going to impact the fault current? Most faults on the power system are like sync VARs. So how's that gonna work with like volt VAR enabled or constant power factor mode enabled on the DER itself? So and then plus VAR coordination issues. This is a really serious issue. If you just like enable volt VAR with just no coordination amongst inverters or DERs in general, you can actually, these functions can do more harm than good to your distribution system. And the reason for that is for volt VAR curve, I really don't have those slides because it was kind of like outside the scope of this presentation. The slope of volt VAR curve, or the setting of your, even the constant power factor, like, you know, the setting that you pick for your power factor, these are all location dependent. Okay, so if you're closer to the substation, you're going to end up having totally different setting for your voltage regulation schemes than the end of the circuit. And then the other point is, like, these, you know, these facilities need to coordinate when it comes to pushing VARs to the grid or pulling VARs from the system. Having just autonomous operation of these devices doing the voltage regulation without any coordination can cause voltage flicker and other issues in the system, like voltage instability on the distribution system as well. So we are reviewing, we're working closely with EPRI and some other organizations to come up with a good methodology and how to adopt voltage regulation, which can actually increase the hosting capacity of our system for DER. But again, the focus would be to resolve these issues when it comes to like coordination. And the other thing I should mention, when you have a generator A connected to a distribution wire with a particular volt VAR setting, and then you have generator B connect to the same circuit, it's going to, and with volt VAR enabled, it's going to impact the settings of customer A. So you have to go back and change the settings of customer A. Imagine this, then you have like, hundreds, 200s, thousands of DERs on your distribution system. There's no way you can go back and change settings. And there's no guarantee that, they're all going to be on tomorrow. Some of them may be offline for maintenance. Some areas there's cloudy and there's not enough generation to keep the generators on. So the concept of DERMS and advanced DMS, that's where I'm going with, that you need to have that sort of automated process in place so that these smart brains, the technologies, monitor the status of the generators and then send the right command setting commands, to the generators that, to adjust the settings based on the existing condition. And in 1547, we mandated the interoperability requirements and the communication requirements. So all new DERs, regardless of the size and type, will have the communication capability. And that's what we really need for voltage regulation and some other grid support functionalities. So because of that, we're still in the process of adopting voltage regulation. We have some more discussions to go, but we're hoping that soon those will be adopted in the state. And last but not least, the frequency regulation. Right now, we're using the frequency regulation for like passive anti-islanding protection. Basically, we have a screening for an anti-islanding protection in the state for areas where, a portion of the distribution feeder is isolated or substation is isolated from the rest of the grid. All DERs within that island should trip off within 2 seconds. Some DERs that utilize passive anti-islanding protection, like rotating machines, may have issues with detecting, like on-time detection of the island if the frequency regulation is enabled, because once you do have the frequency, like active power mismatch in the island, which impacts the protection, which impacts the island frequency, with frequency regulation enabled, the DERs will try to regulate the island frequency rather than trip, which is not what we want to see on the distribution side. So this is something that also that we're also discussing. There are other functions under 1741 SA that you see here that for now they're off, like specified power factor, volt VAR function, watt VAR priority, and all that. So these are off for now. The only thing is on is the ramp rate. So we pick 2% of maximum output per second as the ramp rate, and so we're gonna. But again, we're working on the rest of the requirements under 1741 SA. So this is in addition to the right-through that I mentioned that is mandated. So one last thing I should mention on right-through, the requirements are currently mandated in the state, so all DERs, when I say all, only inverter technologies, I'm sorry, that, for solar generators, regardless of the size, they have to comply with our new requirements. And we worked with inverter manufacturers to create like a New England package of the settings so that during commissioning, the developers can just enable that package and it has all the settings that are specified in New England. And the process was a bit timely, but we made it work. It was quite an interesting and experience, and we learned a lot of lessons when it comes to changing a particular setting, we know who to talk to and what the process will be. With that, I will. That's basically my presentation, and I can take a few questions. So, Charlie, I'm not sure if you have any questions, but I'll turn it over to you.
Okay, thank you, Babak. We have a few questions that have come in. I'll just remind people that there's a Q&A box down in the lower right-hand corner. Please feel free to submit your questions, and we'll get to as many of them as we can. The first question is really a set of two questions, Babak, and they're related from two different people. The question is there an inherent conflict between momentary cessation and PRC-024, and how should the industry plan for this conflict? That was the first question. And the second question, follow-up, was, but some grid codes require injection of current during the fault. If the smart inverter stops providing current, it will not comply with this request. I believe that's a European grid code consideration. So I guess the basic question for 1547 has to do with the question of whether there's an inherent conflict between momentary cessation and PRC-024.
Yes, that's a really good question. So we are currently working with NERC on that. Yes, there's a bit of conflict there. That basically, having inverters not produce current may not be helpful when it comes to grid stability. So, you're momentarily losing that inverter, right? So, from when it comes to supporting the grid, you definitely need power generation, current generation. So the answer, again, is yes. We're working closely with NERC and see what needs to be done on the PRC-024 standard. But the idea is, again, you see where I'm going with that. The ideal case is let's not even do momentary cessation and it's just like have the stay on, produce power, support the grid. On the other hand, there are now issues on the distribution protection side, and we do not have that sort of like high-speed protection, that we like fiber stuff that we have on the transmission. So if you did have the high-speed protection on the distribution, definitely you can utilize different types of protection and not let this right-through concept adversely impact it on the distribution side. But unfortunately, we don't have that, and that sort of high-speed protection, and that's a challenge for us.
Let me just ask a quick follow-up question, Babak, and that's on the momentary cessation capability. Is there something about the nature of the inverter design that requires that capability there, or is it something else?
No, this is more like, inverters can, if you look at this, I'm sharing the slide now, just point number 2, you can go down to basically 0. So inverters can actually, by nature, they can provide current at voltage below 50% also. It's more like, the requirements that we're seeing on the distribution side, the impact on system protection that requires this type of function.
Yeah.
Otherwise, they can do that.
I mentioned for those on the call too that there's some good work that NERC has done in this area in the last 6 months, really stimulated by the PV trips during the Blue Cut and the Canyon 2 fires. And there's a series of webinars that NERC and the North American Generator Forum and ESIG produced during the summer that are done now, but they're available on the NERC website for those who are interested in more depth in this, as well as a recent NERC report. So a couple of other questions here. A very specific one on slide 12, Babak. What is the rule for the range of 61.8 to 62 on slide 12? I guess it looks like there's not anything between 61.8 and 62.
Yeah, it's may ride through or may trip, really. You know, if you look at the you know, the settings, there's always like a white area where you have you know, may ride through, may trip. So that's basically where we have what we have for this table.
I don't quite see that on the chart. You'll have to take a closer look at that. Question about Massachusetts. Do the new ride-through standards require changing settings on existing inverters en masse, or do they only apply to new installs?
Only applies to new installs. We set a date of March 1st for any inverters or any solar applications that we receive after March 1st, and that are like larger than 100 kilowatts. And then June 1st was the date that, you know, any solar applications received on or after June 1st, regardless of the size, will comply with the right-through requirements.
Okay. And a question on the voltage levels. Does the implementation cover all voltage levels, or specifically which voltage levels on the distribution grid are covered in the implementation?
All distribution voltage levels, yes. So we have 4 kV systems, 13.2, 13.8, all covered by this requirement.
And in the standard, how high does the standard 1547 go for voltage?
So the standard, we really did not put any sort of voltage classification in standards. We also removed that 10 MVA cap. We're just saying the standard applies to the distribution system interconnection. The reason that we couldn't do voltage classifications, like some utilities consider, you know, even 115 kV as their distribution wire. They may have some directly connected load, and like for us, National Grid, our maximum distribution voltage is 13.8, and then we go to like 23 kV and 69 kV for subtransmission. So we really we're not able to come to an agreement on the voltage class. We kind of just left it open, but we specifically mentioned that this standard only applicable to distribution systems, and then that will be at the utility's discretion to say what that distribution voltage is.
Yeah, so maybe this would be a good time just to mention the PAR for 2800, Babak, just so people know what else is going on.
Yeah, definitely. That's a good point, Charlie. So we received a request to, we meaning like on the PES technical committees, we received a request from an entity in China to develop a guide for solar interconnection and transmission system. And then that name was changed to inverter-based interconnection. And also, we also created another guide. So this was like P2800.1, and then we created another one, like a P2800, to address that from performance perspective. So 2800.1 was mainly, the testing and making sure the inverters meet certain requirements, and then 2800 is the from performance perspective, what are the requirements? And so we'll be both PARs receive good support from PES technical committees for sponsorship. And we're hoping that we'll have good guidelines for these interconnection of large-scale solar to a transmission system. But that's something that needs to be coordinated with NERC guidelines as well.
Good, thank you. We've got a few minutes left here. I don't see any specific questions in the box, but I'll ask a couple others that I think people might be interested in, Babak. One is the difference between 1547 and the Hawaii Rule 14H and the California Rule 21. Could you say just a few words about what the major differences are and if there's any plans to try to reconcile them in any way?
So Rule 21 and 14H can be considered as requirements that are like a portion of 1547. definitely the standard itself is, the requirements are a lot more, I would say, substantive than Rule 21 and 14H when it comes to, say, voltage regulation capabilities, when it comes to select frequency regulation state capabilities, consecutive right-through events, so all this 1547 covers, includes what's in California and Hawaii. I haven't seen, California and Hawaii folks or utilities having any plan to adopt 1547. I'm hoping that they'll start the process pretty soon, because what they have right now with the smart inverter settings, that's not for 1547. There's a lot more than that. And for example, I'll show you this. This is from 1741. Specified power factor or volt-var function. We have, under just reactive power capability, we have 4 different modes of operations for voltage regulation. And that's something that, California and Hawaii need to create a process to adopt the standard for.
Okay, thank you.
Yeah.
I guess one other question, Babak, and I've seen numbers from 1547.1 all the way up to, I don't know, .7, 8, 9. I don't remember now, but you mentioned the .1, the testing standard that was going on. What else is going on in the family of 1547 standards? What should we be looking for?
Yeah, so that's a good question. So 1547 and all its families, I should say from .1 to .9. So from .2 to .9, they're all guides or recommended practices. They're not standards. For example, I'll just give you an example. From 1547.2 is the guide. If you're, if there is a requirement in 1547 itself, and you need some guidance on, you as the utility need some guidance on how to meet those requirements, you can refer to 1547.2 as a guide. You don't have to comply with it all the time. It more helps you meet the requirements in the base standard. So from .2 to .9, they address many aspects of interconnections, interconnection itself, the interconnection studies, microgrids or islanded systems, 1547.4. And there's more, the only dot that we don't have right now published is .5. We also started the revision process for .2 as well. So the part was, project authorization request was approved by IEEE SA, and we have the teams actually ready to start the revision process for .2. We also created a new dot, I should say, 1547.9, which will be a guide for interconnection of energy storage. So the current version of 1547 right now, the one that the standard that is published, addresses energy storage or applies to energy storage interconnections, but we needed a dedicated guide for that because there's a lot of discussions going on, when it comes to energy storage deployment, and so the working group felt like, we need a guide like that, and we have PAR is approved. We have assigned a lead for that PAR as well, and we're going to start the project pretty soon.
Okay, a lot going on there. Thank you, Babak. Well, we're about at the top of the hour, so we're going to need to wrap it up. And as I mentioned earlier, an email will go out once the presentation and audio file have been posted. I want to let you know that we appreciate your engagement and look forward to seeing you at our next webinar, which will be Tuesday, September 11th at 1 p.m. Eastern. The webinar will feature John Wellinghoff, a former commissioner and chair of FERC and founder of Grid Policy, Inc. John is going to discuss the strategies for implementation of federal legislation and FERC orders dealing with the transmission planning process, specifically looking at alternatives to conventional transmission, including distributed PV, energy storage, and direct load control, using a case study from the CAISO process. And with the rapid development of PV, energy storage, and DLC on the distribution system, I think this is a very timely topic. and I hope you'll be able to join us once again. Further information on all of the webinars and meetings can be found on our website at www.esig.energy under events and in our newsletters and informational emails. Babak, I want to thank you very much for this timely and informative webinar, and thanks again to all of you for your participation. We look forward to seeing you again next month. Thank you and take care.
Thank you.